A warm welcome to all of you. Today we are going to understand how a neural network predicts house prices. This network has a special structure called 4331, which means input layer is having 4 neurons and 2 hidden layers. In each hidden layer, 3 neurons and 1 neuron in output layer, which means it has 4 layers working together to make predictions. Let's start by looking at the structure. You can see 4 purple circles on the left hand side. These are our input neurons. Each one represents a feature of a house. The size in the square feet, number of bedrooms, age of the house in years, and a location score. These are the basic facts we feed into our network. Moving right, we have 3 teal colored circles forming our first hidden layer. Think of these as the network's first level of understanding. They are connected to all 4 inputs through gray lines. Each line has a small yellow number. These are the weights, which tells us how important each connection is. Some weights are positive, some weights are negative, showing different relationships between features. Further right, another set of 3 teal circles forms our second hidden layer. This layer processes the information from the first hidden layer, creating even deeper understanding. Finally, on the far right, we have one pink circle, our output neuron. This single neuron will give us the final prediction, whether the house price is high or house price is low. Notice the red numbers above each neuron in the hidden and output layers. These are the bias values. Think of bias as a baseline adjustment that helps each neuron make decisions better. Every neuron expect the input has its own bias value. Now let's see our network in action with a real-time example. Above our input neurons, purple numbers appear 0.8, 0.6, 0.4 and 0.9. These are normalized values representing a specific house, fair, large size, moderate bedrooms, relatively new and excellent location. Watch carefully as the forward propagation begins. Yellow pulse appears at the each input neuron and starting traveling along the connections. They pass through 3 times to emphasize how signals flow through the network. This repetition helps us visualize that data is actively moving and being processed. As the yellow balls reach the first hidden layer, those steel circles light up, showing they are now active. On the right side, you will see the title hidden layer followed by a mathematical calculation. Z is equal to sigma of I is equal to 1 to 4 Wixi plus B. This is the fundamental calculation each neuron performs. The sum of weights times inputs plus bias. Below, the activation formula appears. A is equal to sigma of z is equal to 1 by 1 plus e to the power of minus z. This is the sigmoid function that transforms our calculated values. Let us focus on the first neuron in hidden layer. The detailed formula has been given. H1 of 1 z is equal to w1x1 plus w2x2 plus w3x3 plus w4x4 plus b, which is bias. When we substitute the actual numbers, we will get the a final z value, which is z is equal to 0.789. Then applying the sigmoid activation function, a is equal to sigma of z is equal to 0.789. Above the neuron, a yellow timer starts counting from 0.00, which it incremental value 0.02, 0.05, 0.10, climbing smoothly like a stopwatch until it reaches to 0.79. This timer visualizes the computational happening in real time. When it finishes, the final value 0.789 stays above the neuron in white. The same process repeats for the second neuron also. H2 of 1, z is equal to w1x1 plus w2x2 plus w3x3 plus w4x plus bias. And finally, we can able to calculate the z value. Z is equal to 0.409. The timer counts up again from 0.407 above the second neuron. Similarly, it will follow for third neuron also, and its z calculation 0.628, and similarly it will try to calculate all other neurons also. The calculation shows for remaining all hidden layers. As the box appears next to the output showing high price with a confidence score of 62%, since our output is above 0.5, the network predicts this house will be expensive. The box pulses to draw attention to this important result. Now let's understand the sigmoid activation function better. A graph appears showing the characteristic S-shaped curve. The formula sigma of z is equal to 1 by 1 plus e to the power of minus z. The sigmoid function maps any input value to a smooth range between 0 and 1. This is crucial because it gives us probability we can interpret as confidence levels. But how does the network learn? This is where backpropagation starts. The title changes smoothly. If you can see, error calculation will appear. Error is equal to output minus target, which is showing 0.620 minus 0. The error 0.620. Our network predicts 0.620, but we wanted 0. The error is 0.620, the difference between prediction and target. Watch as yellow balls now flow backward through the network. They move from the output back to the second hidden layer, then the first hidden layer, and finally back to the input. Each backward passes happens 3 times, just like forward propagation, emphasizing the flow of error information calculation. This ensures weights move in the direction that error reduces. Our 30% error reduction in one iteration demonstrates this learning in action. The key features that made this visualization effective includes the dynamic timer showing values counting up from 0, step-by-step calculation with actual number substitutions, and a clean layout preventing text overlay. Most importantly, we say the complete learning cycle from making a prediction to improving through error correction. This neural network is now trained and ready to predict house prices. By processing the 4 input features through 2 layers of learned patterns, it can estimate whether a house will be expensive or affordable. The continuous flow of information forward for prediction and backward for learning is the essence of how neural network works. Remember, what we see was just one training iteration. In practice, we can repeat this process through thousands of times with many different houses, allowing the network to learn the complex relationships between house features and prices. Each iteration makes small improvement, and together they create a powerful prediction system. And finally, this is how neural network learns to solve real-world problems by processing information forward to make predictions and flow error backward to improve their weights. This is the beauty lies in the simplicity of mathematics and combined with the power of repetition. Thank you.